Welcome back. This is video lesson number 12. Today we're going to be talking about positive series tests. So we're going to go through 3 tests that we use to determine when a positive series converges or diverges. So when I say positive series, all I mean is a series like this, sum of an, where each term is a positive number. Okay? So everything we're going to be talking about in this video doesn't necessarily work the way you want it to if you have a series for which some of the elements are positive and some of the elements are negative. We have other ways to handle series like that we'll talk about in, in class and future lessons. But for now, we're going to assume all of our series are positive. By the way, I will use this symbol, sum of an, to refer to a series where I don't care about where it starts. So like n can start at anything as long as it goes to infinity. So when I write sum of an without the limits, you're assuming that n starts somewhere that doesn't really matter and goes to infinity. So it's an infinite series. So here's the first test that we're going to be talking about. It's called the integral test. So we start with some series, that's of course a positive series, and we assume that the terms of our series are given by a continuous decreasing function. So we have some function f of x, and to get the terms of our series, we're plugging in whole numbers into our function. Just like with sequences, not every series is of this form, so you can't always use this, which is important. But anyways, what we do is we have a function and we can integrate it because it's continuous, and so we take the indefinite integral from 1 to infinity and see if that converges or diverges. And the integral test says if the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. So to check the convergence or divergence of this series, all we need to do is check the convergence or divergence of this improper integral. Here's an example. As promised in the previous video, we can see from this test that the harmonic series diverges. And the reason for that is because using the integral test, if I look at the integral from 1 to infinity of 1 over x dx, we know that this diverges, right? It's a p series with p equal to 1, and we know that those diverge. Okay. So here's some exercises to get you comfortable using the integral test. Go ahead and pause the video and give them both a shot, and then I'll go over them. So the first thing we need to do is write down the function that we're using. F of x equals 2x over x squared plus 1 squared. So this is a continuous function for x bigger than 1, at least, and it's definitely positive. The only thing we need to check is that this is decreasing, which I'm not going to do. The way you would do that is by taking the first derivative of this function and showing that it's less than 0, right? Negative first derivative means the function is decreasing. So you can do that on your own, but you should always make this check when you're doing the integral test. Anyways, now I do the integral from 1 to infinity of f 2x over x squared plus 1 squared. And we can replace the infinity by a limit as r goes to infinity. We can do a substitution. We can say here this is u is x squared plus 1, and then 2x dx is du. So we're finding the antiderivative of 1 over u squared. That's going to be minus 1 over u. So I'll just write that. So we kind of just did that in our heads, or maybe you think I'm skipping steps, but this is the antiderivative. And I'm evaluating from 1 to r, and so I get the limit as r goes to infinity of, I can use this minus sign to switch the limits, so I just have 1 over 2, which is what I get when I plug in 1, minus 1 over r squared plus 1. And as r goes to infinity, this term will go to 0, and so I get 1/2. Meaning that the series, meaning that this improper integral converges, which means by the integral test that the series converges. Now, it's important, I'll just mention this, that you don't put any weight on the value of the integral. Just because the value of the integral was 1/2 doesn't mean that this series sums to 1/2, okay? So we would have said that if that were true, but it's not. From the convergence of this integral, we get the convergence of the series, but the value of the integral is not related to the value of the series. Next problem, for which values of p does the p series, which is 1 over n to the p, converge or diverge? So this is just like the harmonic series, we just look at the integral from 1 to infinity of 1 over x to the p dx. And this converges if p, remember this is from a previous lesson, this converges if p is greater than 1 and diverges if p is less than or equal to 1. So this is going to be the same answer here for this series as it is for this integral, just using the integral test. So I wrote this as an exercise, but this is actually something you should remember and keep in mind, because these are very simple series that we know just based on the value of p whether they converge or diverge. So we'll use those later when we're doing comparison tests. Speaking of which, the next test we're talking about is the direct comparison test. If you remember the direct comparison test from when we were talking about improper integrals, it's almost exactly the same for series. So the setup is, suppose we have two sequences, an and bn, for which, well, an is less than bn eventually. So there's some m, a number such that after, if I'm looking at terms of these sequences after that point, I have an less than bn. This is just really saying I don't care about what happens for the first few terms or the first, finitely many terms of these sequences. I only care about the end behavior. So after some point, I require that an is less than bn. And just like in the integral test, I get the following. If the larger series converges, then the smaller series converges. So being smaller than a convergent series means you converge. And if the smaller series diverges, then the larger series diverges, meaning being larger than a divergent series means you diverge. Here's a quick example. I have the sum of 1 over square root of n times 3 to the n. I notice that 1 over square root of n, 3 to the n, well, this square root of n, as long as n is bigger than or equal to 1, square root of n is bigger than 1, and so this, multiplying the denominator by square root of n makes the entire value smaller, because I'm making the denominator larger, and so I get a smaller number overall. So 1 over square root of n times 3 to the n is less than 1 over 3 to the n. And since the sum of 1 over 3 to the n converges, remember it's a, it is a geometric series. Right, with r equal to 1/3, which is less than 1 in absolute value, that means that this series converges. Okay, so if you were comfortable with the comparison test from improper integrals, then this is almost exactly the same. If you are uncomfortable with it, then this is another opportunity to get some practice with it. Right? This is, in fact, we'll probably be using the direct comparison test more here for series than we did for integrals. So here's some exercises. Use the direct comparison test to show that each of these series either converges or diverges. Okay, so for this first one, I notice that n over n minus 1, if I ignore the minus 1 in the denominator, meaning look at n over just n squared, I made going from here, from left to right, I made the denominator larger by getting rid of the minus 1, and so I'm going to get a smaller number, right? And this is equal to 1 over n. So what this shows is that this series is larger than the sum of 1 over n, which we know diverges. And so by the direct comparison test, right, remember, bigger than a divergent series means you are divergent. Okay, For the next one, I do the same thing where I try to simplify the denominator and see what happens. It turns out if I ignore the n here and look at just 1 over e to the n, I'm making the denominator smaller, and so I get a larger thing here, right? The denominator here is smaller than it is here. And 1 over e to the n, right, if I look at the sum of 1 over e to the n, this converges because it's a geometric series with common ratio 1 over e, which is smaller than 1 in absolute value. And so my series 1 over n plus e to the n also converges. So the last one starts from the observation that the natural log of n is always less than or equal to n, but for n greater than 2, it's always less than. And so if I take reciprocals, I get 1 over ln n is larger than 1 over n. And so it's the same comparison that I had up here. I'm showing that my series is bigger than the harmonic series, and the harmonic series diverges. So I can just say 1 over ln n diverges. If you wanted to write more, you say by direct comparison to the harmonic series, or you write because this series diverges, the series in question diverges. Okay, here is the last test. This is a new one. It's called the limit comparison test. So here's what we do. We take two positive sequences, an and bn, and okay, before I write it down, we're interested in the sum of an and the sum of bn as infinite series. But we just consider them as sequences for a moment. We take the limit of their ratios, and if this limit exists and is a positive number, so it's not, I should also say that right, it's not infinity and it's bigger than 0 and the limit exists, then I get the following. If one of the series converges, then the other one does, and if one of the series diverges, then the other one does. So actually you can switch A and B here too. In other words, the series either both converge or both diverge. So the idea is I have some series that I want to find out whether it converges, and I find another series that I know converges or diverges, and compute this limit. And if I get a positive number, then I can use the knowledge of the first series to get knowledge about the second one. Here's an example. Here's a series for which if you try to do direct comparison, you get stuck because you want to really compare to 1 over n squared, but this is a larger series than 1 over n squared, and so the comparison test won't help you, or the direct comparison test won't help you. But instead, we compare to the sum of 1 over n squared. So what do? We take the limit of the ratio of these two sequences. So I take the limit as n goes to infinity of 1 over n squared divided by 1 over n squared minus 1. And it doesn't matter which one is on top and which one is on the bottom for this. I get the limit. So if I simplify things a bit, I can flip all of these. So n squared minus 1 comes into the numerator, and n squared goes into the denominator. And this limit is 1. Okay, so this converges. This series converges. And so the series that I asked about must also converge by limit comparison. Okay, here are a couple exercises for you to do using the limit comparison test. So give them a shot and then we'll go over them. So the way that we find out what we should be comparing to for limit comparison is by kind of ignoring the insignificant terms in the numerator and the denominator. Here, this means ignore the minus n squared minus 1 and just look at n squared over n to the 4th. And that simplifies. So the idea is this should be similar to the sum of n squared over n to the 4th, which is the sum of 1 over n squared. So I'm going to compare to 1 over n squared, meaning I take the limit as n goes to infinity of 1 over n squared divided by n squared over n to the fourth minus n minus 1. After I simplify things, so this n squared goes into the denominator here, this goes into the numerator, I get the limit of n to the fourth minus n minus 1 over n squared times n squared is n to the fourth. And then, well, we can see this limit is 1, and just like before, since this converges, my original series must also converge. Okay. For the next one, we do the same thing. Ignore the insignificant terms in the denominator, meaning ignore the plus 4, and we get the sum of 1 over n squared cube root, meaning n to the 2/3. So this diverges. So we expect that our series will diverge. But this is not enough to just write squiggly lines and then a series that you think is similar. You actually should compute the limit. Even if it just feels like we're just writing things down that we already knew, we need to be careful about it. So the series I'm comparing to is 1 over n to the 2/3, and the series I was given is 1 over cube root of n squared minus 4. So we can either observe, well, actually we should simplify first. We get the limit of, we have n squared minus 4 to the 1/3 over n to the 2/3. So, okay, you can see that this limit is 1 either by, you could do L'Hopital's rule if you don't believe that the limit is 1 just by looking at it. You can compare leading coefficients. You could divide the top and bottom by n to the 2/3 and see what happens that way. Anyways, you get 1, and so this series has the same convergence or divergence as this series, meaning that the series I was given, cube root of n squared minus 4, must diverge. Okay, so that was a quick run through of the integral test, the direct comparison test, and the limit comparison test. We'll see more series tests for not necessarily positive series in class in the next lesson. But for now, it's important to be comfortable with all of these. We'll have lots of opportunities in class to practice them, and you can always find more in your book if you're looking for them. So as always, let me know if you have any questions, and I'll see you next time.